Alrighty, folks, welcome back from lunch. Thank you again to our sponsors for providing that. Hopefully you guys all enjoyed it. We had a good time at the newcomers' lunch as well. A lot of good attendance there, nice faces. So why don't you go ahead and get settled in. Once again, it's open seating in first class up here, just like Southwest Airlines. Come on over to open seating, get a table, meet some friends. And I wanted to introduce Christoph from Apple, who's going to talk to us about TCP Fast Open.
Thanks for the introduction. I'm coming from Apple, and we have been working on an extension to TCP whose goal is to reduce the latency and basically improve the user experience when accessing the internet. However, in this talk, I'm giving you basically a tale of all those issues that we found with deploying this solution. We have had a lot of issues with firewalls and mailboxes, intrusion detection systems that were completely blocking our extension. And so this talk can be seen as like a call to action that in the firewalls and intrusion detection systems, we should try to take TCP Fast Open into account so that solutions like these can be deployed in the internet today. So let me first start with why does latency actually matters? In the number one metric that we are using mostly to advertise and also to measure our internet connectivity is the bandwidth. But how much does the bandwidth actually matters in terms of user experience? So there was a study in 2010 that measured the page load time of the 25 most popular websites when the latency is fixed at 60 milliseconds and the bandwidth is varying from 1 to 10 megabits per second. The study has shown that when the bandwidth increases from 1 to 2, there's a significant increase or a significant benefit in terms of page load time. However, when the bandwidth increases beyond 5 megabits per second, the benefit in terms of page load time is basically non-existent, it's marginal. The major influencing factor for page load time nowadays with the high bandwidth that we have nowadays is basically the latency. The study has measured the page load time, again, for the 25 most popular websites when the bandwidth is fixed at 5 megabits per second. And as you can see on the graph on the right side, as the latency decreases, the page load time decreases as well. And so there's a linear correlation between page load time and the latency. Now, the question is, why is this actually? Why does the latency have such a high impact? Well, it's because the websites that we are accessing have many different web objects. And as we are fetching the index.html, we discover, oh, there are actually other dependencies for this website. And then we have to establish a new connection to maybe a completely different server and fetch this other web object. And all this back and forth between the servers is affected a lot by the latency in the network. Now, the page load time impacts basically the user experience, and the user is not very happy when the page load time is taking a lot of time, is basically very large. And there was a study in 2013 at IMC which measured basically the impact of latency on service revenue. And the study has shown that only 100 milliseconds of additional latency in the page load time has a significant impact on the revenue and customer satisfaction. So this means basically page load time should be the number one metric that we use to evaluate our networks because it is impacting user experience, user satisfaction, and ultimately it is impacting also the service revenue. Now, to understand why does the latency has such a high impact on the page load time, we have to look a bit on the protocols that are being used on the internet. So the TCP, the Transition Control Protocol, is used for 95% of the internet's traffic, and it provides a reliable and in-order byte stream. So all the web objects and everything is being sent over TCP. Now, in order to provide this reliable and in-order byte stream service, it requires a so-called three-way handshake. And the three-way handshake is there to establish a connection and negotiate some parameters for this connection. Now, this three-way handshake has been under a lot of criticism in the past, and it has led to the so-called TCP joke, where basically somebody wants to wants to hear a TCP joke, the other side confirms, yes, I'm going to tell a TCP joke, and actually the TCP joke never starts. And that's basically what TCP is. It is a lot of back and forth between the client and the server before the useful data can actually be sent. So this TCP handshake is actually very expensive. The client is sending a SYN to the server, and this SYN contains the sequence numbers and some options to negotiate certain extensions for this connection. And the server replies with a SYNAC to this SYN, confirming the sequence numbers, acknowledging the SYN being sent by the client, and also confirming also the TCP options. And only after this process, the client can finally send its data request to the server, and the server can only reply. So as you can see, this handshake basically takes one RTT. Now you might say, well, one RTT, that's not so much in the end. However, on cellular networks, RTTs, or on congested networks, RTTs can go to several hundreds of milliseconds sometimes. And as I have shown in the introduction, only 100 milliseconds has already a very significant impact on the service revenue and on the user experience. So if we would be able to cut down this TCP handshake delay, we would have a major benefit for the users of the networks. Now, luckily there is a solution to this problem available. It's TCP fast open, standardized at the IETF under RFC 7413. And it's basically an extension to TCP to accelerate the TCP handshake. So what does it do? TCP fast open allows basically the client to send the HTTP request, or maybe the TLS client hello, together with the SYN at the same time. As the server receives this SYN together with the HTTP request, it can reply immediately with data, sending it back to the client. So as you can see, by using this kind of method, we are cutting down the latency of the handshake. However, of course, there's a downside to it as well, that if we would do this in a very naive way, it would open the door for denial of service attacks, because attackers could basically flood the servers with IP-spoofed SYN segments that are requesting for a lot of data. So TCP fast open includes also a security mechanism to protect against this kind of behavior. And I will show you later how exactly these mechanisms works. Now, thanks to the benefit that TCP fast open provides, at Apple we decided to deploy it in the iOS 9 and OS 10.11 release. And it has been used for an Apple service on all devices. And the API that we deployed for this is also public, and we are basically expecting that in the future a lot of applications will start using it. And so the traffic, or the TFO traffic on the internet will increase more and more, and it will gain more and more popularity. And overall, we saw that this was very beneficial from a user experience point of view. However, firewalls got also in the way, and sometimes they were very destructive to the connectivity of the client. And in the remainder of this talk, I will tell you more about those issues that we found with respect to firewalls. So first, I'll need to do a little deep dive into the details of TCP fast open to see how it really works. So it starts off with a cookie exchange. Basically, the client is sending inside the SYN a TFO cookie request to the server. This is basically to negotiate support for TFO. The server, upon reception of this, generates a cookie, which is basically the hash of the client IP with a local secret. By doing it that way from the server side, it is completely stateless. It can always regenerate a cookie. Why is it using the client IP inside the cookie? What it is to protect against the denial of service attacks. That way, an attacker who is spoofing IP addresses cannot attack the server, because he doesn't know the cookie that it would correspond to the specific client IP. And the server then, when he has generated this cookie, he will send it back to the client as part of the TFO cookie option inside the TCP option space. Now, the client has learned the cookie that has been provided by the server, and he can use this now in order to send the HTTP request together inside the SYN. And as you can see here on the graphic is the client does this together with the TFO cookie. The server, as it receives this SYN with data, he can verify the cookie, so it is protected against the denial of service attack, and he can read the data, and finally he can reply with a SYNAC acknowledging the reception of the data, and he can send the response immediately. So as you see here in this graphic is that we are not losing time anymore due to the three-way handshake. We are replying immediately with the data, and we are gaining several hundreds of milliseconds in terms of latency on networks that have a high delay like cellular networks. Now, as I mentioned, we had a lot of problems with middle boxes. And I'll give you a little overview of all those issues that we found and why we think they are there and what could maybe be done to circumvent them. As a summary, we found middle boxes and firewalls that respond very badly to unknown TCP options. We had middle boxes that were dropping TCP packets because of those unknown TCP options. We had middle boxes who removed them out of the option space. We also found other middle boxes that were even more destructive, that were like marking entire connections as invalid. So the client was basically being completely blocked. Other intrusion detection systems went even one step farther. They were even blocking the full client, so the client didn't have any connectivity to the internet anymore for a certain time period. We found it went from 30 seconds to sometimes 90 seconds. And so this kind of behavior is, of course, very destructive and is kind of a showstopper for TCP fast open. So let's start with the first middle boxes. Well, TCP fast open is using a new TCP option. And we have found middle boxes who are removing unknown TCP options. Now, how does TFO behave in such kind of behavior? Well, if the client is sending its SYN with the TFO cookie request, the middle box will remove it. The server will receive a SYN without a TFO option. And he will assume that this is a regular connection and he will not generate a cookie inside the SYNAC. From a performance point of view, this is not that destructive because basically the client will have to fall back to regular TCP. Clients who are in such kind of networks will they will pay a latency cost compared to other well-behaving networks. And so they will have a worse user experience. Now, the question is maybe also, why are those middle boxes and firewalls removing those TCP options? Because using an unknown TCP option, it's not necessarily an attack vector. It's maybe just a new extension to TCP that is being deployed. And so in our view, middle boxes should not remove those TCP options. Another issue that we found is basically sometimes they not only remove the TCP options, they drop the SYN segment entirely. Now, when this happens, the way we react in terms of TFO is we are retransmitting the SYN after a retransmission timeout of 1 second, and then we are not using the TFO option. Now, if we have such kind of middle box in the network, this increases the latency by 1 second, and it has a very huge impact in terms of user experience, because every connection will take 1 second to be established. So the user experience is significantly degraded. Now the question is again, why would the middle box drop those kind of segments that have an unknown TCP option? Because dropping is like the most destructive operation that could be done, and it has a very big impact in terms of page load time. Also, similar behavior for the SYN segments that are containing data. We saw middle boxes that drop those segments as well. And we have, again, the same behavior in terms of user experience, where we are retransmitting the SYN option without data. The user is paying a significant and very big latency cost. Some more tricky middle boxes that we found were basically when the server receives the SYN together with the data, he acknowledges the data as well. And so the acknowledgement number is higher than for regular TCP. So let me show you a little bit this more in detail. The SYN segment, for example, has sequence number 0, and it has a data level length of 10 bytes. Now, when the server receives this, he will acknowledge this, and the acknowledgement number will be 11. Now, many middle boxes might say, oh, I expected acknowledgement number 1, and so it will drop those SYN_X segments. And the thing is, the server will keep on retransmitting the SYN_X segments. He will think, no, I have received up to 11 bytes, so I will acknowledge 11 bytes. And the mailbox will keep on saying, no, you should not acknowledge 11 bytes. And the mailbox will still keep on expecting only 1 byte. And so what happens here is the connection will never be established. And basically, the client will not be able to browse the internet at all, unless we are able to kind of detect those behaviors and turn off TFO. And so this is very disruptive in terms of user experience, again, because from the client's point of view, the internet is down, the network doesn't work. Another issue that we also found in one of the mailboxes is that some intrusion detection systems were completely black hole in the client. And it was really interesting to see the behavior that we observed there. So basically, the client is sending a SYN with data, and he adds the TFO cookie option. The server received this SYN plus data, and he responds with a SYN_ACK acknowledging the data. And the mailbox that we were experimenting with, it didn't drop this SYN_ACK. And even the server replied with the data immediately, and the client received this data. So everything looked fine from a client point of view. Only after that, the mailbox started blocking the traffic. And it actually blocked not only this particular connection, it blocked the whole client for a certain time. We saw from 30 seconds up to 90 seconds and sometimes a bit longer. So this kind of behavior, again, is very disruptive. It's basically a showstopper for TFO. And those networks were basically one of the major reasons why we in the end decided that we'll have to turn off TFO. So the question is, how common is this? Well, it actually mostly TFO works. It works rather in 80% of the cases. However, if I, as a user in my home, I'm in a network that doesn't support TFO, 100% of my connections will not work. Yeah? Or 100% of the users of a particular network provider of a particular cell in a network, and if there's this mailbox, their internet connectivity will be less good and less performant than in the other well-behaving networks. So to conclude is basically latency has a direct impact on the user experience. And TCP fast open is a solution that would allow to significantly reduce latency. Those mailboxes, however, are kind of interfering significantly with the deployment of TFO. And we would like to make a call to the vendors of mailboxes, firewalls, and all these equipments, and also to the operators, that we should take TCP fast open into account, experiment with it, and make sure that it works in the networks, because it will allow for future extensions of TCP, and it will also allow to improve the user experience. So if you are one of the network operators or the equipment vendors, you can come talk to me after the talk to discuss on how we can verify and validate that TFO works correctly in your network. Feel free to come talk to me. And with that, I would like to thank you for your attention, and I'm ready to take questions.
Yeah. Tony Tauber, Comcast. So there isn't a quick way to test it, see whether it's working in different scenarios?
There are some tools available that allow to explore whether, for example, there are mailboxes that remove TFO options, like Tracebox. Maybe you've heard of this tool. And besides that, it's possible to, Linux supports it, and also in many, since quite some time. So it's possible to create a connection and see if it really works. On our side, we would like to work on a tool that allows to validate that your network works on this, but at the moment I cannot yet confirm that it will be available. But we can talk later on how we can make sure that TFO works correctly in Comcast.
Yeah, well, I mean, not asking just for myself, but anywhere.
Anywhere, yeah.
I mean, if if you had a website, well-known website that you could just say, hit this and it'll confirm, like the dancing turtle thing, like, you've reached this via.
Yes. So basically,
TFO.
I think if you go to google.com, it has TFO enabled. But yeah, that's one of the websites you can contact if you are using TFO on the client side.
So you're saying that if TFO is blocked, you won't be able to get to Google? Or you'll have
It all depends on how it all depends on how it is blocked. So if you have if there's one of the mailboxes that is blocking the client, one won't be able to access this website. If it is a mailbox that removes the TFO option, what iOS and OS X is doing is basically in the retransmission of the SYN segment, it won't use the TFO option, so it will fall back to regular TCP. And so what is currently needed is one needs to actually really look at packet traces to understand whether TFO is working. Tracebox is a tool that actually allows to see which TFO option, which option is being removed in the network and which box is actually doing it. So I really recommend to use Tracebox for those kind of measurements.
Thanks.
Yeah.
Matt Petak, Yahoo. So you're talking about TCP options a lot here. Did you do any comparison of V4 versus V6 behaviors with middle boxes? First question. Second question, do you have known vendors that are problematic that you could let us be aware of we should look for on our networks? Or is this we prefer not to name, but here's a tool that you might be able to use that will tell you if your middle boxes are not happy boxes?
So with respect to V4 and V6, unfortunately, we don't have any data on this. So if there's a difference between V4 and V6, so we don't know. We haven't gathered this kind of data. With respect to naming vendors, I don't want to point fingers and name the vendors. We have worked with some of them who acknowledged, yes, oops, this was a bug, literally, and they fixed it in a later version. However, we don't know where this old version is still deployed, so it's difficult to say. Then we also worked with some network operators where we really found those issues. Some were cooperative and tried to fix the issues. Some were less cooperative and were like, this is the way the network works. So yeah, with respect to the tooling, at the moment, there's no tool yet available. As I said, yeah, get in touch with me after the talk and I can help you out on how to validate for TFO.
Can you clarify, did you mean you didn't test with V6 or you just don't have a comparison between?
We don't have the data.
Oh,
we did test. We did use it on V4 and V6. In the data collection process, we didn't separate between both. Yeah.
Philip Matthews, Nokia. I'm just wondering if you could perhaps use this as a chance to encourage people to do this by you use the fast TCP fast open option on addresses that work well, and you don't use it on those that don't, and therefore people who are used on certain providers get fast and others get slow, and so it's sort of a natural incentive for people to improve their work.
Yes, maybe, yes. Well, like if we would have such kind of a list of which operators or networks are well behaving, we could blacklist and whitelist on the server side. Absolutely. So if anyone wants to come on the whitelist, okay. Thank you very much.